Hello, my name is Feldbrugge and I will be talking about recent work I did on the catastrophic universe. This will be work in collaboration with Rien van der Weijgaard, Benjamin Hertz and Maya Rodriguez. And I will be talking about what makes a wall and a filament in our cosmic web. Cosmology in the late time universe is often can be phrased in terms of how we go from very simple initial conditions, as we, for example, see in the Planck data, to the fully nonlinear structure we see in redshift survey, which is known as the cosmic web, with big empty voids, dense clusters of galaxies, two-dimensional walls and one-dimensional filaments. And the big question I will be addressing today is what makes these walls and filaments? Can we identify patches in the initial condition, in the Gaussian initial conditions, that will later on grow on to form the walls and filaments in our universe? And what is their mathematical structure? How can we use that to understand the cosmic web? So the cosmic web can be understood in terms of caustics due to the nonlinear gravitational collapse which we see. So on the left here you see a two-dimensional embodied simulation. You see that we start with a homogeneous distribution of particles, but as the cosmic web forms, as the gravitational collapse takes hold, you see the formation of these multi-stream regions. So for example, you see here a multi-stream region where you have three different initial positions ending up at the same final position. Where you go from a single stream region to a triple stream region, or from a triple stream region to a five stream region, you expect a caustic. And indeed, if we plot the caustics, where basically the dark matter stream turns around in red, you see that, and we see in the upper left plot, we see there are no caustics. In the upper right plots, you see the creation of the first caustics. And then in the lower two plots, you see that the fold caustic, the red line, nicely bounds the structure. This is also known as the shell crossing regions. And the idea is that if you can track the geometry of these caustics, you can track the geometry of the cosmic web. So these folds are the first of the caustics we will consider, but as you will see, there's a list of caustics which corresponds uniquely to the different elements of a cosmic web, so the walls, the filaments, the clusters. And by studying these caustics and their formation history, we hope to understand the cosmic web to a better extent. This is not a new idea. So in the 80s, Zeldovich and Arnold and Sergei Shandarin were the first to attack the cosmic web, trying to understand the cosmic web from a mathematical perspective using catastrophe theory. And they did a beautiful job at this, but they could only do it in 2D, unfortunately. So look in particular at the third paper, 1982, which is a beautiful paper describing how the different geometric features form in our cosmic web in the two-dimensional universe. How does this work? Well, you take the Lagrangian fluid dynamics perspective, where you send initial particles to their final positions. So let's Q be the initial position, let S be the displacement field which the particle has experienced in time t, and let xt be their final position. Then what you can do is you can derive the density of this Lagrangian fluid in the following way. So if you want to know the density ρ at time t at a position in the Eulerian space in our current universe x prime, then what you first need to do is you have to find the initial positions which map to this final position. So that's given by this inverse mapping, also known as a pre-image. And then for every initial point which maps to x prime, we have to calculate this determinant. So we take the displacement map, and we take the Lagrangian map, we take the gradient, then we take the determinant. This gives you a volume form. Then you take the absolute value to make sure that it's always a positive volume and not a sign volume. And then the density is the density of the initial state divided by this volume. So that's given by this formula. And with a little bit of linear algebra, you can simplify this formula to read the following formula. So here you see that we have a determinant of a matrix, but using the eigenvalues of this matrix, so using the eigenequation, which is below here, you can rewrite that as the fraction of the mean density divided by 1 plus the eigenvalues. And one thing which is really striking, which you can use to interpret this, is that when 1 plus mu is 0, you divide by 0, you get an infinite density. And this is the first example of a caustic. So you can see it in the upper right figure, where you see that the density spikes to infinity when you go from a single to a multi-stream region. And this is the first caustic, but you can also have other caustics, for example this A3 caustic, which is known as a cusp caustic. And catastrophe theory and the theory of caustics is a classification of these caustics, which I will talk about. So up to recently we could only do this in 2D, but now we can finally do this also in 3D. And what you will find is that not only the eigenvalues, but also eigenvectors play a key role. So what you can do is you can take your initial conditions of structure formation, let's assume that to be a Gaussian random field. And what you can do is you can take a model of structure formation. Here we will take the Zeldovich approximation. And from the Zeldovich approximation, which we can take as this x, we can study their caustics. So we can take the gradient of the x map, and we can calculate the eigenvalues and the eigenvectors, and then what you find is that you can identify the fold, the cusp, the swallowtail, the butterfly, the umbilic, and the parabolic umbilic caustics. And these are the only ways in which you can form these singular features in a stable fashion. So this is a classification of the dynamics which happens in these structure formation processes. It's very nice to have this algebra because it gives you a very precise definition, but in the end we would like to have geometry. So what you can do is you can say, well, these different caustics have different dimensions, and then they can be associated to the different geometric features we see in our cosmic web. And what we will see is that the fold caustic, the A2 caustic, correspond to the collapsed regions. So that's in accordance with what we saw before, where you see that the red lines are bounding the collapsed regions. Then you find the cusp caustic, which is the higher order one, which takes this form, where you see that you take the directional derivative of the eigenvalue field in the direction of the eigenvector field. That has to be 0. And that corresponds to the walls and membranes of the three-dimensional universe. Then you have the swallowtail caustic, which correspond to filaments, but also the hyperbolic and elliptic caustics, which corresponds to filaments. And then finally you also have two caustics which corresponds to clusters. So how can we use this? The first thing to realize is that we can predict the geometry of the cosmic web from the initial conditions using these eigenvalue fields. So if you take the upper left panel here, then you see the Gaussian random fields representing the density field. If you take the upper right panel, then that's the corresponding gravitational potential. If you take the gravitational potential, you calculate the Hessian, its eigenvalues, then you find the eigenvalue fields, which are the left and the right lower panels. And what you can see that in the lower panels, you can already see a lot of the spider web network which we see in the cosmic web. And indeed, these eigenvalue fields are a very nice tracer of the nonlinear structure which occurs and forms during gravitational collapse, which we know as the cosmic web. We can push this a little bit further, so we can run the Zeldovich approximation, which is just this linear approximation of structure formation and an embodied simulation, and we can apply it to the same initial conditions. And what you will see is that initially these two models are the same, but then at some point the Zeldovich approximation will break down, whereas the nonlinear structure formation really kicks in. And if we now take the eigenvalue fields and the caustics of the left plot of the Zeldovich approximation, then you get a skeleton of the cosmic web based on these caustics in the initial conditions, which is known as Lagrangian space. So that's this network which you see here on the left, where you see the red line is the fold and the blue line is the cusp. If we now take this embryonic skeleton of our cosmic web and push it to Eulerian space using the embodied simulation, you see that everywhere where your eye would identify a filament, you will see this blue line. So you see that the cosmic web can indeed be captured using these caustics. But we would like to push this a little bit further, and in particular also run constraint simulations. So Gaussian random fields are a multi-Gaussian process, and there is a very nice property which this process has. So it's a Gaussian distribution, and this Gaussian distribution has the property that if you set linear constraints, so if you say that you have, for example, two-dimensional Gaussian distribution, and you say the second variable x2 is a value a, which is a linear constraint, then the resulting distribution for x1 is again a Gaussian distribution where the mean has shifted, but the covariance matrix is altered in a way which is independent on the value of a. And this has traditionally been used to constrain Gaussian random fields. So you can say, let's create a Gaussian random field which has a peak in the center or has some other linear constraint imposed. Recently, I managed to extend this to nonlinear constraints, where we can now impose these Gaussian, these conditions in terms of the eigenvalues fields and the eigenvector fields. What you basically have to do is you have to do it in two steps. You first build a small dimensional model which captures all the nonlinearity, which is this constraint manifold, and then subsequently you can constrain this using the linear procedure after you have sampled this. So now finally let's address the real question. What makes a filament, what makes a wall? If you take the cusp conditions, then they take this form, where the formation time, the cusp condition and the orientation. And this works quite well to some extent. So you see on the background the embodied simulation, in blue you see the constraints. However, there are two big problems with this picture. If you take an initial position, you are more biased to end up in a cluster because these attract matter. The filament is stretched in the filamentary part and is compressed in the clusters. Moreover, in the cluster you see that the fault line, the cusp line piles up. So again, this is not a place where we trust our models. So what we are proposing to do is to add a second set of conditions to this, which is here on the right. And this condition basically requires the filament to be maximally stretched around a certain point. So you have a kind of a midpoint of the filament, which we call the center of the filament, which experiences maximal stretch. And that corresponds to the second eigenvalue field being negative, the first derivative of the second eigenvalue field in the second eigenvector direction has to be 0. And the second order derivative in the second eigenvector direction needs to be positive. And if this is true, then we have indeed a stretch of the filament, and it can be between the clusters or a filament which is probing out into the single stream region. If we now implement this using Hamiltonian Monte Carlo constraints, then what we find is that we can run embodied simulations and see how these features, how these initial conditions with these very simple nonlinear constraints lead to different structures in the late-time universe. So if you set up these conditions and set the scale at which these filaments form, the formation time at which these filaments form, and run the embodied simulations, then you see that you get a filament every time in the center of the box where the dotted black lines cross. And this is a very nice result because now you have control over the formation of these filaments from the initial conditions. So you have complete analytic understanding why an element becomes a filament or doesn't become a filament. If you would do something similar but then using traditional ways of identifying filaments, then you could say, well, let's consider saddle points in both the primordial density field or primordial gravitational potential and do this exact same game. So we set these saddle points in the density field or in the gravitational potential, and we evolve the embodied simulation and see what happens. And what you find is that if you take a saddle point in the primordial density field, there is some correlation with the filaments, but it's not a very strong correlation, and sometimes you even end up in a cluster. Moreover, the orientation is not really well specified. And this shows that there is more to filaments than just saddle points in the density field. Note moreover that you are unable to set the formation time using the saddle points method. If you take the gravitational potential, then you see that there is a stronger correlation with the filaments. So you see that in the lower plots. However, still you are not able to specify the formation time. So it could be that you are considering a mass element which will form a filament in the future rather than in the past, which would not be really what we expect when we look at the cosmic web. So using these constraints, we can nicely classify the different filaments in these two-dimensional models. But we would like to go beyond the two-dimensional models, of course, and consider the cosmic web in its three-dimensional glory. So if you extend these ideas of considering the cusp and the caustic conditions and then looking for the points which are maximally stretched in the direction along which the manifold runs, then you can define specific center of walls and center of filament conditions in the initial conditions. So what you find is that the cusp wall, defined by the first two conditions, need to be augmented by a set of conditions which I've listed here, which again require maximal stretch. For the umbilic filament, you find that there is again a very simple condition you have to add. For the swallowtail filament, it turns out that you have to do a little bit more work and you have to impose these additional conditions. Again, you have a condition here that it's negative, that means maximal, that it is stretching, and then the other condition corresponds to maximal stretch. If you now impose these conditions, then you can run embodied simulations and you can see what happens. So here I've set the condition at the green point, and you see that the green point is on the wall and it's exactly in the middle of the wall. It's at least at the point of a lot of stretch, which is really nice. So we can extend the work I just described in 2D to 3D. If you do it for the swallowtail caustic, then you get this line. So the blue line is the swallowtail caustic, and it's nicely in the middle of a filamentary structure. So if you look at the white, you would identify this as a filament. So it's really nice that we now can specify some local conditions in the initial conditions and then retrieve the filamentary structure in the late-time universe. If I do the same for umbilic filament, I get a very similar picture. Note that the umbilic filament will be denser than the swallowtail filament and form at a later time. So their formation history and the local environment and the geometry and the formation time is different, but they are both one-dimensional line-like features, so we would identify them as filaments. So with this I would like to conclude. So I hope that I have convinced you that we can classify the cosmic web using caustics, and that this will require both the eigenvalue fields and the eigenvector fields in order to really understand. So the eigenvalue fields give you the fault, the eigenvector fields give you the higher order caustics. This classifies the geometry of the cosmic web based on formation history rather than morphology. We can identify conditions which correspond to protowalls and protofilaments, and we can now run embodied simulations with a nonlinear extension of constrained Gaussian random field theory. And I really hope that we can in the future use this to improve our understanding of all kinds of parts of a cosmic web. So I hope that we can, for example, use this to, in more detail, and refine the study of galaxy alignment and spin alignment and shape alignment of galaxies. But I also hope that we can use this in the end to understand redshift surveys, because whereas endpoint correlation functions are very nice and predictive and well defined, they are not necessarily the best way of capturing the geometry of the cosmic web. And since these caustics are geometric in nature and tied towards the geometry of the cosmic web, this could be a very promising way of retrieving the geometric data from embodied simulations in the end. But there's yet a lot of work to be done before this is, of course, possible.